Welcome to ARVN, Amateur Radio Video News. The program you're about to see is free to watch, courtesy of YouTube. Thanks, YouTube. But it wasn't free to make. ARVN's got a lot of money invested in video equipment like this sweet camera and that editing system back there. And it takes a lot of time to shoot and edit a program like this. So I'm asking you to make a voluntary payment, contribution, whatever you want to call it. Just stop by our website, arvn.tv, and you'll see a link to make that payment, whatever you think the program is worth to you. I guess you could say that this program is brought to you by you. So thanks for watching and enjoy the show.
Okay, well, good morning. Good to see everybody here today. A couple of questions before we get started. Does anybody in the room here use digital voice over HF? All righty, well, okay, here's one gentleman over here. I know he's heard me on the air. So, all righty. I'm going to talk a little bit about how we got to where we are today and what's in store for the future, which I think is quite bright for us. So I'm going to talk about a system called Digital Radio Mondial. Mondial is a French word for meaning broadcasting to all. This is a digital replacement you'll see for AM as shortwave, medium wave, and long wave as we know it today. And we'll talk about these other applications, the last one being a hardware implementation, and the first three are in software. I'll talk just some real basics here in context with HF digital voice of Y digital, the evolutions I mentioned in software, and a hardware solution, AOR. And then I'll play some demos of digital voice as we're doing it today over the air. So why digital? I think there's a lot of reasons, of course, for digital. We're seeing it more and more today, analog being replaced by digital. But one of the main things, it's much easier to make a decision if you've just got a 0 and a 1 versus an AC voltage or a complex varying voltages. And once you have an 0 and 1s, then you can apply coding algorithms. You can correct errors. They're easier to detect. And the processes of a complex analog signal is quite complex compared to a digital signal. And one of the things you'll find later as you listen to digital voice over HS is noise is effectively lost. And that means a lot to listener fatigue. It's not in the demodulation process and as is found in the analog world. So for the first thing we have to do for digital voice is to get the analog converted. And we do that through sampling. And as George mentioned, there's sound cards that do that for us with the A to D conversion. Each sample represents the wave's voltage level at that moment in time. And that output's into a converter, which turns it into numerical values. That's a very simplistic way of explaining it. But of course, we have to do some more things. We have to encode that so we can efficiently compress it. Otherwise, we would have to have a lot of spectrum to be able to send, say, a wave file over HF. And the reverse of that's decoding. The corresponding voice decoder receives a data bit stream for processing. So how do we do this? Well, we do it with coder decoders. Codecs, as they're called. There's many of these in the world you may be familiar with, like MPEG-4, MPEG-3. But we're looking at an entirely different type of codec, ones that runs at much a slower rate than these that we see typically with a CD, for example. They model speech in small segments, and then they're converted into synthesized speech signal, which is perceptually close, or we hope it will be perceptually close to the original. The parameters for speech, level, frequency, response are extracted and then encoded into a bit stream. And typically some of these that we're using on HF is linear predictive coding 10. This was at one time a standard that the military used. It's since been replaced by another one called MELP, multi-level excitation level. And we've seen speech being used over the internet. and it works quite well at higher bit rates, but we found it will work at a lower bit rate as well. So we've tried and are using these codecs today. The problem with codecs is the intellectual property, and that's another issue that we hope will be completely past us in the near future, and we'll have a very good codec that will give us some good audio over HF that will be in the open source community. Now here's a typical digital process. This is a graphics from AOR. I used to do quite a bit of talks in supportive of AOR, a hardware method of doing digital voice. But this gives you a stream of both the input and output. We're using a ADC through what they call AMBI, their vocoder here, which is a codec, and then to an OFDM modulator, and then to another DAC and output to audio. And then just the reverse of that, where you have your receive audio coming in an ADC, back to an orthogonal frequency division multiplexing. I'll talk a little bit about OFDM, back to the vocoder, convert it back to analog, and then out to the speaker. I've got quite a few slides here, so I'm going pretty fast. So I thought I was going to have a little bit more time, but I'm going to be squeezed a little for time. But I want to get through these basics, and then we'll look at some of the software. So applying these this digital process to HF, then we've effectively got rid of noise. And another problem that we have with an analog, of course, is the QSB fades. They're eliminated. So we reduce the listener fatigue. And Kurt talked a little bit about earlier in his, some of you may have been over there with the FCC about realizing the benefits through narrowing the RF spectrum. We found that we can do this and have pretty good voice quality in half of what we have with sideband today. And the other non-voice applications, we can also, along with voice, we can send the call sign to ID, so we don't have to ID. And we can send text, we can send short messages, or we can even send a file and pictures, and we can set up the configuration for the mode that we want to use. We can define how robust we want it to be dependent upon the signal strength and the conditions of HF at the time we're sending. So this software that was first looked at a number of years ago, because DRM's been out over 10 years, was Dream. And we'll take a little look at it and what it involved. DRM, for those who are not familiar with it, over shortwave is gradually, I say gradually, I don't know if it'll ever happen, but it's one attempt to replace AM as we know it today over shortwave with a digital mode. And I think it works quite well. There's a couple of different versions of it. DRM originally was for HF only, but now it's a DRM Plus, which is being implemented for the what we would think of here as the FM bands. It was driven by an international consortium of broadcasters, manufacturers, and regulators, and educators. There's about 100 members throughout the world. DRM is not found here on our soil, but it is found in Europe and Asia and the Pacific region. In the past year or so, we've seen great insights of DRM in China. They're very interested in it because it has a very wide reach, as AM does. And also in the Pacific region now, Radio New Zealand is using it basically as a station link to other FM stations throughout the Asia, Southeast Asia, because they want to be able to transmit through these islands and then convert it back to FM and broadcast it from a central location. And that's worked out quite well. Radio New Zealand does have a tremendous signal here in the United States, and I listen to it often. There was a project called, it was a DRM project in Alaska. And you may have read a little bit about it because the ARRL got a little upset. They thought that they were going to be transmitting within the amateur radio frequencies. That really never happened. But they buried a transmitter down in below ground here, and they were using some of the DART digital Aurora radio technology transmitters and using cross dipoles. And what they were attempting to do, and I think it could have been done, was to cover all of Alaska with a radio signal, which, you know, that's never been done before. And we're probably going to use some of it as a station link to send to other FM stations so they could cover the whole state. Unfortunately, with the economy the way it is today, they lost all their funding, and right now I believe that project's dead. Maybe it'll come back someday, I don't know, but that was the only attempt. There was some work done by HCJB and the VOA for DRM as well. I'll give you some idea of what it sounds like here. See if I got level up here. Let me know if you can hear this okay.
This DRM transmission to the northeastern United States can be heard each day at 2100 hours UTC on 9800 kilohertz.
I'll have some more clips of that. This is from our friends up in Canada. They broadcast daily in DRM. DRM also can provide a journal line that is text with it, and they can also do send pictures, JPEG pictures at the same time. These are actually hyperlinks of news right here. Just click on them, and you can pick up quite a bit of information through their journal lines. Here's some typical stations that I picked up in St. Louis, Radio Australia, Radio New Zealand, Deutsche Welle, stations in Germany. Even Kuwait had a station. They're not on the air right now, but they had a quite strong signal that they beamed to the northeast United States. And here was some work done by the IBB, International Broadcast Bureau, and HCJB for DRM. So how does this work? It uses coded OFDM. OFDM was chosen because it's very robust in multipath, and then Doppler uses quadrature amplitude modulation. It uses a variety of codecs. The AAC is primarily the one used. It's 10 kilohertz channel spacing, which fits real nicely in an AM station, although there is some 9 kilohertz and up to 20 kilohertz of it. And they can integrate images, HTML pages, schedules, and they have different robustness modes depending on the bit rate of their codec they use. So it's a quite effective way of sending a transmission that can be decoded over long distances, which FM, of course, doesn't have that capability. So here's an example of OFDM where you take your base carrier and you're spread out across a bunch of frequencies that are separated. In this case, this is AORs by 62.5 hertz. They're orthogonal. Each one of them stand entirely on their own. This unique spacing ensures this orthogonality of the carriers, and each one transmits a small amount of data on each one. And the baud rate, guess what the baud rate of each one of those carriers is? Something that they learned from ham radio operators 60, 70 years ago, RTTY. They're running at 50 baud. So again, that's the reason why it's as robust as it is. Now, if you look at something like ADSL, it uses these. There's tens of thousands of carriers on them. DRM uses 460 carriers. So as you reduce the number of carriers, of course, you reduce the RF bandwidth. But at the same time, you have to have a much slower codec because you don't have enough data there. Here's a typical DRM signal, a flap top signal. These are their sync carriers right in here. They use 3 of them that run about twice the power. And if you're interested in using something like this with your single sideband radio, well, your immediate problem is how do I get 10 kilohertz wide signal in my sideband radio? Well, I've got a example of how you can do that quite economically. And I'll pass that around here. Also, another digital world radio traveler that I carry around with me. Inside this box is this converter, to give you an idea of what it looks like. You can take this and put it inside your transceiver. Very simple setup. This is typically a 455 kilohertz IF. This fellow also I5XWW makes some for ICOM radios as well. But this works quite effectively. HCJB has come out with a little, it's basically an SDR radio that runs specifically for DRM. It works quite well. And there's some hardware solutions just now coming out of Japan and from Korea. So I think we're going to see a lot of growth in DRM, at least in several countries, in the next year or so. When we first started looking at this program to say how could we use it on amateur radio, we found that they did have a 4.5 kilohertz bandwidth. But basically, the way the regulations are written today, you could run 10 kilohertz on 20 meters, but you probably would run into a little bit of QRM problems doing that, although I did it once. And from that, this is an earlier graphic user interface of DRM. HB9TLK made a few changes in the program, changed the number of carriers that were used, and brought it down to 2.4 kilohertz, and used an LPC codec, which ran at 2.5 kilohertz. And it was able to make some contacts with this. Several of us use this early version of the program. But the problem with the program, it took, it wasn't like a full transceiver. You could either transmit or receive. You had to switch back and forth between applications to be able to use it. So as a result of that, within about, I guess about a year or so later, he came up with WinDRM, which has been a fairly popular program. It used one GUI for both receive and transmit. It carried over some of the robust modes that DRM had. Uses OFDM again from 29 to 57 carriers. And it uses a couple of different codecs, SpeedX, LPC, and another one that we used for a while until the codec cops came after us, called Mel. It's fairly quick too. This also was initially used to send digital pictures. The guys found out that, hey, this does a great job of transferring pictures, and it has a way of correction errors by sending sends in segments, memory segments, and you could use this program to correct those by sending a bad segment report, and it would automatically be received and returned back to the station that was receiving the picture, and would automatically clear that picture up, remove all the errors out of it. So it was developed for ham transceivers, no modification required for this like you would need for DRM. It uses a fast accent channel to transmit the call sign, the type of modulation, the interleaver. This is forward error correction. The bandwidth is being used in the sync pilots. And in its main service channel, it would transmit the actual voice. And again, this was done, we could use from 4 to 64 quadrature amplitude modulation, and also with FEC protection. It has multiple displays for monitoring both the transmit and receive signals. I wrote the documentation for it. It's basically gives you a lot of information on digital voice itself, so it's a good place to go to learn about digital voice and how it works here. Here's a typical waterfall is used for receiving. It's a matter of lining up the pilots under these little red dots, so it's fairly easy to tune in. The problem with this program, if you want to call it that, if you're an AMer, it wouldn't be a problem, but it takes several seconds to sync. And so it doesn't give you that sideband type of experience where, you know, quick turnarounds. It takes several seconds for all these radio buttons to turn on and for the MSC channel to come on and to start hearing audio. But it's quite dramatic when you do hear it. So from that, it was developed. Yes?
Do you have a sample of what this sounds like?
Yeah, I'm going to give you some sound bites. Yeah, it's a little bit easier to integrate them all into this and switch them back and forth. It takes up quite a bit of time. So I'll show you, yeah, definitely show you how this stuff works. Well, DRM was great, but its bandwidth was 2.4 kilohertz, and there was always a strive to get the bandwidth narrower and narrower. And the reason for that we found was we were our worst enemies. That is, my sideband friends were our worst enemies. They don't know what this noise is, which is what they interpret as just band noise or somebody illegal. So, you know, he'd say, well, Bob, you hear all that noise? I said, I think we can talk over that, so we'll just slide down here. There's nobody using this frequency. So it was a real issue, especially when you were 2.4 kilohertz wide. And even though we had good forward error correction, a lot of interleaving, you would still, they would cut out enough carriers if somebody got close to you, especially if they splattered all over you, that you would start seeing dropouts in your voice. And that's, of course, the last thing you want is dropouts, which we've probably all experienced if we've had an HD radio or a cell phone, for example. So G3PLX, who we all know, the PSK31 guy, he was also looking at digital voice, and he wrote a program called DigiVoice. And he used FDM, frequency division multiplexing, and we found that was, you know, was quite effective, and didn't require any sync time. It just synced up like that. So you could actually almost operate Vox with his system, although it was a very early implementation. He didn't follow through with it. Some of us grabbed it over here in the U.S. and started using it. He wasn't too happy with that because he didn't think it should be released yet. So anyway, he just pulled it off, and he said, forget this, you guys. And so Cisco, who wrote FDMDV, and we had it working there. Cisco actually wrote an implementation of an FDM modem as well, but we found that G3PLX was much better, so him and Cisco got together, and lo and behold, Cisco said, here, Peter, can we use your modem? He says, oh, sure, here, says, take the modem. He says, now don't share this with anybody, but you can use it. So, and that's been a little problem later on. Of course, it's basically this program's not open source. And we've even lost track of Cisco, but we're still looking for it. But anyway, this has been a very good program, and it's very simple to use. This squelch control over here will allow, even if you have some dropouts, to come through, because if you can catch, you know, a few syllables of word, you can probably understand what the fellow's saying. This would be in very low signal-to-noise ratios. You have short message service down here up to 55 characters. I'm getting a little bit ahead of myself, but this was developed in December 2007. Cisco, after he saw Peter's work, I think that was in like October, he developed this whole program within about a 3-month period and released it in December of 2007. And this one has a communications voice quality in 1/2 the bandwidth of sideband. It has a fast instant sync on voice. There's no delays whatsoever. It's very robust to noise and QRM down to less than 4 dBs/R. Sideband is 0 or less. So we're getting very close to that. It has an auto ID tuning. So if you're anywhere in the band, if this signal's anywhere in the band pass, using this Reed-Solomon ID. It will automatically put it right on frequency. And it has an AFC, so even if you do have a 10 tech and it drifts a little on you, then that's not a problem. It'll follow it around. And no radio mods, and it's compatible with all sideband radios. So here you can see the carriers of the FDMD. The center one's a BPS carrier with twice the power in it that changes phases for syncing. 14 quadrature phase shift keying carriers are again running at our 50 baud already. There again, 1400 bits per second with no forward error correction. I did talk to KA9Q, Phil Carnes. You all know him. And he said that he could take a program like this and add some forward error correction, which would help and avoid some of the dropouts where the signal just literally goes away due to fading. But until we get an open source codec, he's not interested, of course. A good open source codec, that is. So it has SMS, as I mentioned, where you can enter your call sign QTH. Its spectrum bandwidth is 1.125 kilohertz. And currently we're using the LPC codec, and in the future you're using codec 2. Codec 2's being developed now, and it sounds very good, I think. So I think in the near future, we're going to try to use it with this program, probably with WinDRM at first. So we're looking forward to codec 2. We're using F6 CTE's RSID for mode ID, auto sync. It does have a transmit ALC, and this is to improve the average power. You notice the peaks on OFDM. If you can bring that average power up and avoid the peaks, which can be distorted if you try to run too much power with a sideband radio, that's good. So we did publish a spec on FDMDV. Paul Ronaldo did help me with this, explaining how the modem and its data rate, how we arrive at the 1450 bits. And it also uses, for the text, it uses Peter's varicode, so it's very efficient. So the radio, PC Easy setup, uses the same audio connections, just like PSK31. For voice I/O, though, we need another sound card, and that can be a Logitech USB sound card, or it can be something as simple as this. And this is about a $6, $7 card from geeks.com called a US adapter. Just plug it in, plug in some earphones and a PC mic. That's all you need. You don't need any expensive Heil microphone for this. Real cheap to get into this mode. You can use a rig blaster, or the same type of interface that you would use, for example, with radio or a PSK31. Conventional single sideband mode with no EQ. You want as flat as possible, so you keep all the level of those carriers the same. And we normally run about 25 watts because the peak power will be about 100 watts. Again, there's complete documentation written for this program. It's all here. So I have these programs, DRM and Dream program, on a CD here. I think only have about 20 copies. I don't have enough, but all this information is available on the web as well. Again, the transceiver connections, typical would be a USB headset and a rig blaster or something similar to that for interfacing the sound card to the transceiver, again, to avoid any common noise pickup. Any noise that's picked up in the system, of course, is going to be tried, it's going to transmit and try to demodulate it. And typically it sounds like a bee, a buzz in the signal, and that's usually because they picked up some hum or noise somewhere in their system. Again, the Logitech, there's this little USB card I was mentioning. Again, the system requires, of course, a codec, and this is the LPC. This can be substituted for other codecs. This is all the files here. The whole program, everything's about 130K, so it's fairly complex or fairly simple. Here's the typical setup for it. Using a COM port, put in your call sign, set up your sound cards. There's the author Cisco, HB9 TLK. A new open source code, codec 2. We have David here, VK5 DGR today. He's developing this, and right now it's running at 2400 kilobits per second, so that means we can use it with WinDRM. And its voice code, its voice quality should be as very close to MELP, multi-level linear predictive coding, which we have also been using with this, but it's the one that has a problem with the intellectual property in it. And I feel it's as good or better than Ambi code as well. I might ask David, let's see how much time we got. We got plenty of time. David, would you like to mention just a couple of words about your development on your code? And I'll turn it over to David for just a few minutes here. Because this is the most important part of digital voice, is having a good coder-decoder, because we need to be able to compress this data down so that we can minimize our bandwidth on HF.
Hi. Yeah, I'll be talking on codec 2 later this afternoon at 3:15. I have a background in speech codec development, and I've also been a ham for about 30 years, so I'm really interested in contributing.
Thank you. Really interested in contributing an open source speech codec to the ham radio community. Been working with Mel and a bunch of other people who are interested in speech coding for ham radio. And I guess what I'd like to get out of this conference and some feedback from everyone is what we need to do to drive this forward. What would really make you guys excited about using digital radio, digital voice in particular, over ham radio. And that could be HF or VHF. And I think one of the key steps is to get some of these open source components together. As you can see, the software landscape's a little bit patchy. There's some developers who've come and gone, missing source code, things like that. So we need some people who can work all together to produce a new mode, and I think the outcomes could be really exciting. We've already seen that Mel's using modes here that use half the bandwidth of single sideband. We're getting close to the signal-to-noise ratios required for single sideband, so I think in the future we might be able to come up with modes that are better than analog modes for digital voice and really push the hobby forward that way. Anyway, I'll be talking some more on codec 2, and I'll have a fairly basic introduction into what's a fairly complicated algorithm, but I think I've broken it down into a way that pretty much anyone can understand, and I'll be talking on that at 3:15 this afternoon. Thank you.
Thank you very much, Peter. I'll give you some idea of what's coming up. It's very exciting for us in the digital voice world, obviously, because we were using this MELP code, although that's freely available to the military and a lot of other people, and it was paid for by your tax dollars. It's still got a lot of intellectual property. There's several companies involved with it. So we, in respect to that, we are no longer using it most of the time. So let's see, and what's the hardware alternative to all this is the Authority on Radio. I'll pass that around. See this? This little box here, which uses the Advanced Multiband Excitation codec. It was first introduced here at the conference in Phoenix, I believe it was in 1999, 98 or 99, and by G4GUO. And here was his card, his implementation of it. He was running on, I'll play a little soundbite on an old ICOM 706. It was open source software, and it was a predecessor of this box that I'm centering around right now. This is G4JNC, talking with G4GUO.
Yes, G4GUO from G4JNC, and in case you're recording this is using the 36-tone modem 36C software for the initial voice transmission between G4JNC and that's enough to record it with. Over.
Now that was 1999. This is 2011, so you see how long it's taken us to get to digital voice. It's been a very slow and difficult period, and really this has been because of the codec. There's just not been any available in the open source world. The AOR does work. It worked quite well. It has excellent speech quality. It has a nice PC command set. You can also use it to send digital pictures as well. It has no DRM capability. But of course, the drawback of this modem was $500. That was a lot of money for him, for him to try a new mode. I talked to AOR in quite length about this. I said, we need to get this cost down. And he said, okay, we'll get it down. Well, they didn't get it down far enough. It was, we're still looking at several $100s, even for this one here. Now, you can find some of these on eBay and much cheaper, but this is works quite well too. I mean, there's no problem with the voice quality, although it's not as robust as we'd like to have it. It's 2.4 kilohertz wide as well. But it suffers in robustness. It does take a fairly strong signal, about S9 signal. Of course, we don't always afforded that good a signal.
Mel, quick question. Why the feature of no DRM compatibility?
Well, because it's entirely different. It uses QMSK versus OFDM. It's entirely different. So it can't decode it. No.
So it's not a feature, but it's
No. Right.
Okay.
What I meant by that, a lot of people ask me, well, is it compatible with DRM or WinDRM? I said, no, not at all. Amazing also is the audio spectrum bandwidth. This was measured by K2MO of signals off the air. A little bit difficult to read those, but we were getting better than 3 kilohertz audio bandwidth if this is true what we're seeing here. But anyway, the resultant of it, as you'll hear in some of the audio, it's quite good. Support for this is from N1SU. He has all of the software for this digital voice that I'm talking about today on his site. We do have some nets on Saturday and Sunday on 14236. We chose that frequency because it was relatively close to where the digital pictures were being sent by EasyPal. And as a result of that, we had a lot of fellows from there moved down to find out what all that noise was about and joined us. Codec 2, there's a URL for that. There is a DVD that was done by us, ARVN, and that goes in quite depth on AOR and WinDRM. And DRM-DV was another mode, although it's not being used now, that was a digital voice only. I'll show you a sample of that though. That used the MELP codec and also on D-Star. So I'm just going to speak a few minutes here about this new mode by WA6NUT. It's called FDM-DV Plus. It's a sound card-based mode which enables simultaneous audio and video using HF transceivers. Uses narrowband TV software by ZL2AFP, which is modified to allow 15 FDM-DV carriers, subcarriers from 975 to 2025 in the baseband. This, again, it uses FDM-DV software from Cisco. Other software required is WinWarbler, virtual audio cables, and this priority software. This is what its spectrum looks like from 387 to 3617, which means this spectral, the bandwidth of this signal is 3.6, and he may even have to widen that a little bit more. So I'm a little bit of question, how this is going to play out on HF. Probably 6 meters and above, this would be something you could play with. But we've found that it's got to be a pretty narrow signal to be robust enough and avoid interference on, say, the 20-meter band. But anyway, it's good to see someone experimenting in this, because so far no one else has done it. It's not a very good representative as video, but Terry's video, and he's also got some audio going on at the same time. This is Wind Warbler over here, and you can see these extra carriers on both sides of it. There's some current information on it. He's got a Yahoo group, Rick Peterson, WA6NUT. So it's something you may keep your eye on. Maybe we'll see it, maybe we don't. I'm not even sure the regulations on use of this. I know there may be some problem with this having both modes. I know there's a problem of sending text at the same time with with digital voice, or not necessarily with digital voice, but with a voice mode in the sideband segments. But anyway, having said that, it's still something that we have someone experimenting with, and hopefully something good will come out of it, because it'd be really nice, on HF, to be able to talking with someone at the same time seeing their picture sent. So that's what he's working towards. All righty, so now comes, where the rubber meets the road here. What's all this sound like? So let's take a look at some sound bites. First, I'll give you a little bit more on DRM. We've got still a few more minutes, I believe. This is the BBC. This is recorded from my ham shack here.
Pessimistic sign that oil-rich Nigeria has model schools without electricity. But Mrs. Ogbona's school,
this is not necessarily a real strong signal either, only S9 for a broadcaster. That's not a very strong signal.
Back in Nairobi, as Kenyan architect,
he's running the second service here, which is the data journal line.
His father, Daniel.
So you're going now to the area where you were actually brought up as a child?
Yes, this is where I grew up. I grew up in this house.
Should we jump out and have a look?
That's right.
So here we are.
Go to those links. They're sending the news here.
Houses, they're all now surrounded by high walls and metal.
Your OFDM signal. You see these are what these notches in the waterfall is a result of complete signal loss right here, but you'd never know it. And that's, fortunately, they have a lot of forward error correction, a lot of interleaving. As far as, I don't think I'm getting some distortion from the speakers, so I'm not really realizing how good audio this is capable of. Here we're without a lot of fading. You see a big signal here. This is broadcast daily. There's 2 hours of music. You can see their codec's running at almost 21 kilohertz. There's their constellation. And we're going to be, looking at a codec that's 1/10 of that. Well, there's a lot of screens on the signal. And there's their bandwidth, their spectral audio bandwidth, 13 kilohertz. That's pretty good. I'll go on here. I'll give some examples of WinDRM. That was the first program that I showed you. It was on 15 meters.
Change somehow, switching to this program. I don't know if that affected the gain on your microphone, but it sounds a bit low. So let's see what you sound like on the next one.
Flat top with
K0PFX K2MO.
about 2.4 kilohertz. I've got some more here. I'll run you another one. You notice no noise, no fading.
Or listen more closely, but I kind of like the way the audio sounds coming through the computer speakers. So, I really don't need to have these earphones connected to my my temples.
FDM-DV.
Off my ears, not around my neck, but they are off my ears. So, kind of looks silly right now. Mel, over.
1.2 kilohertz wide.
What codec was that running?
That was run the MELP codec. I've got some more that are run the LPC here. Now here's an example of all three codecs.
On the flex.
This is much rougher.
Showing over 100 mils on the SP200. The noise you're hearing when I stop talking could be the speaker. I have one of them amplified speakers. It should be getting louder as I can turn it off. Very faded out.
And here's LPC. This really doesn't sound too bad.
Well, there are a couple of orange spots in it there, but not bad. I thought you were sounding pretty darn good here for LPC. Yeah, it made a difference, but it sounds a whole lot better with the RM here than it.
And this is actually MELP right here. There's nobody from the FCC here, is there? A lot of notches. They can be quite robust in DX. Yes?
What do these things sound like if we're tuning up the band and we don't have the equipment to listen to?
Oh, okay. Yeah, I think I skipped over that. I'll show you that here in just a minute. So here's FDM-DV running the LPC codec. Now you'll see it's off frequency right now, and he's going to send this TXID, and you'll see it jump over, so it automatically syncs to the signal.
And this is M1FFX in Sterling, Massachusetts, with the LPC codec. K0PFX, I'll copy over there, M1FFX.
Well, that's a pretty neat feature. A lot of times you have to worry about a digital mode. You know how you get these guys tuned in? No problem here. So we'll do a little comparison with FDM-DV with single sideband now. He's on sideband. Almost fading out. Here his signal's coming up. I'm opening up the squelch. I went over to make sure he's in sync.
Yeah, I'm running average power here right now. I would say about 14 watts.
Now what is SNR over here?
Delta loop for 20 meters.
4, 3. It doesn't start falling apart to about 3, so that's real good, I think. Anyway, we're getting close to sideband there. Oh, here's a program called Digital Radio Mondial Digital Voice DRM-DV, and this was an improvement on the first WinDRM. It was a digital voice only program. Oops, that's the wrong one. Hang on here. This one right here. This is with OE3GBB in Austria, and K2MO in New York recorded this. You pay attention to the SNR as he changes power. So, and he's starting out at very, very low power.
5 watts.
5 watts?
This is now. This is
1 watt.
111. This is 5 watts. This is 10 watts. This is 20 watts. And okay. This is 20 watts. This is 50. This is 100. And this is 200. So that's enough, I think.
You see how?
So, if you get my 1 watt transmission today and 1 watt the SNR, and has been dropped out, tell me, taking a few voice.
See, power didn't make a lot of difference in that transmission. He was down to just a couple of watts and we're still able to copy and decode him. Here he is again.
Yeah, okay. I'm back, but I'm still
You had to drop out?
Somewhere being in a low position. And
Another one? He's down to 2, 3 SNR.
The power. Unfortunately, I could read you quite good now. You have been 100% decoded here with about Net7.
QRM.
And Gary, you are a little bit in the QSB, selective QSB, so it's not so good and a little bit lower. I'm running now quick environment. So I don't know if it's linear, but it's some strange amplifier. Okay, I give it back to Mel.
There's your signal.
Copy, so it's with DVD, standing by, over.
Again, it can be a fairly robust mode. Okay, we'll take a look at AOR.
It does have good audio. The AOR does good. Okay, here we are sideband. I'll switch to digital now. And now we're on the AOR. I'm using the 9800 this evening, but there's really no difference in the audio quality that I found between the 9000 and the 9800. So back to you and see how you're copying. K0PFX, Mel Whitten K0PFX.
You can see that's quite good audio, but it requires a fairly strong signal. And if it loses sync, it does have a way of forcing sync, but it doesn't always work. So sometimes you can lose the whole transmission because you're not in sync. I thought of a number of ways to fix that problem, but AOR never did implement any of those, so we got what we got. But with decent signals, it does work quite well. Well, that's all I have. Oh, you wanted to see what it sounded like when you're tuning across it. Let me find that.
Might help some of us avoid the QRM when you're.
Yeah, well, that would be great. Yeah.
Look for you.
Let's see.
Yeah.
Is there any reasonable capability of providing a bit-error rate so you can have a better view of what your signal is?
Here's what it would sound like if you was tuning across it. So it's not very sideband friendly. Anybody that hears that would say, "What the hell is this?" You know, and they would think, "Oh, this is not supposed to be here."
Just another digital mode?
Yeah, just another digital mode, and having no idea what we're doing. And despite we did a lot of PR work for the mode. Steve, the editor of QST, wrote an article about it one time, and we've had it on a lot of websites. But So far, well, we did have pretty good growth there for a while. We have a group, a reflector. One time we had over 500 guys that was monitoring it, and you know, active hams on digital voice. But when we lost a good codec and had to use that LPC codec, most all of them went away. But we still have a handful of guys that get on the weekends. So I have the program here on a few CDs. If not, you can get it from n1su.com's website, and we'd certainly welcome you to join us on the weekends or during the weekdays. There's usually a few guys around. A lot of them just sit there and monitor, you know, waiting for a digital voice signal to come along. So that's all I have. Any questions?
And you kept talking about all the different codecs. Can the stuff automatically detect which codec you're using? Do you have to know it?
Yes, it does. Right. WinDRM, you can select them. There's you can check which one you want, and one of those channels in WinDRM automatically sends that to the receiver and says, "Hey, I'm using Speaks or I'm using LPC." Do the same for codec too. Yeah. So. Okay, if no other questions, again, thank you very much. Appreciate your time today and hope to see you on Digital Voice.